Elementary particle quantum number is the interaction and decays of the hundreds and resonance form what seems to be a bewildering array. Order can be brought into this situation by assigning certain quantum numbers to each entity and establishing which of these numbers are conserved and which can change in a given process. We are already familiar with two such quantum numbers which each describe a particle's charge and spin. These quantum numbers are always conserved, and one set of quantum numbers is used to characterize baryon and the three families of lepton. A remarkable theorem discovered early in this century by the German mathematician Emmy Noether states that every conservation principle corresponds to a symmetry in a nature. In general, a symmetry of a particular kind exists when a certain operation leaves something unchanged. A candle is symmetry about a vertical axis because it can be rotated about the axis without changing in appearance or any other feature. It is also symmetry with respect to reflection in a mirror. The simplest symmetry operation is translation in space, which means that the law of physics do not depend on where we choose the origin of our coordinate system to be. Noether showed that the invariance of the description of nature to translation in space has a consequence the conservation of linear momentum. Another simple symmetry operation is translation in time, which means that the law of physics do not depend on when we choose t equal to 0 to be, and this invariance has a consequence the conservation of energy.
Okay, now we will see the conservation law of the leptons number. We know that there are 6 leptons number, which is electron, muon, tau, electron neutrino, muon neutrino, tau neutrino, as well as our anti-lepton. Lepton, we have electron antineutrino, muon antineutrino, tau antineutrino. So this part is to explain why the beta negative decay release the electron antineutrino but not the muon antineutrino. So I will explain this part. So this is the first reaction, which means on the left side neutron. For the right side, we have proton, electron, and electron antineutrino. So the value of the lepton number is 0, 0, plus 1, negative 1. When we add up, it will equal to 0, which means it will be conserved and occur in our nature. So the second reaction is show that it does not occur in our nature, which means neutron will convert or decay into the proton, electron, muon, antineutrino. So the value is 0, 0, plus 1, 0. So it does not make sense because 0 not equal to 0. So which is mean this not equal to 0. So it does not occur in nature or not take place in nature. So it will not conserve. Okay, next we go to this part. This part is to explain the decay of muon. So we come up with the concept of muon leptons number. This table. So this is reaction. So this reaction is show that it's occur in nature. Why? Because from the left side, the value is 0. And for the right side, the value is negative 1, positive 1. We get the value from this table. This table is already given. So when we add up this ratio, we will get 0. So which means it's occur in nature or it will take place in nature. Lastly, we go to the last part. The last part is to explain the tau lepton interact on the subatomic level. So we came up with the concept of the tau lattice number. So this table, and then this part is the reaction. Reaction is show that the positron, when the positron combine with the electron, the value for the left side is 0, and for the right side the value is positive 1, negative 1. This value is get from this table. So when the 0, when we add up, it will get 0, which means is occur in nature and take place in nature. And this is a conservation law of the tau lattice numbers. Okay, now we go to see the conservation law of the baryons number. Baryon is a particle that made of 3 quarks, including proton, neutron, antiproton, and antineutron. So let's look at one example. So let's suppose proton will interact with the neutron. When the proton will interact with the neutron, during that process, it will produce proton, antiproton, and antineutron. So the combination of proton and neutron, it will get the positive 2, and during that process, after that, they get the proton and antiproton and antineutron. The value is positive 1, negative 1, negative 1. We get this value from that table, and when we sum up, we get the negative 1. So when the value before positive 2 is not equal with the after negative 1, so we show that as a result, this particle this particular reaction does not take in the nature. So the conservation law of the baryons number is important for us to use to determine whether this reaction is occur or not occur in nature. Okay. Strangeness number is denoted by S. Strangeness number is conserved when any subatomic particles interact via the strong force. So this is an example. So let's look at the part reaction 1. The first reaction will show that when the proton is meet up with the antipion or interact with the antipion, it will produce the strange particle here. Strange particle is lambda and K particle. The value from the left side is 0. The value for the right side is 0. For the left side is 0. Negative 1, positive 1, it will become 0. So when 0 is made, this reaction is occur in nature. For the second reaction, it shows that when the proton interact with the antipion, the value is 0. For after that, this it will produce K particle and neutron. Positive 1, 0. This is a value. And when we sum up, we will get the positive 1. So 0 equal to positive 1. So it's not occur in nature. Additionally, so whatever the strangeness value for this particle is also came up with the opposite strangeness value, which means the antiparticle for this antiparticle for this. Like I will give you one example. So this lambda have the negative 1, the strangeness value, but the opposite strangeness value is positive 1. It can be the opposite strangeness value.
Before we go through the Eightfold Way, let us revise what is hadron. Hadron is a subatomic particle, including baryon and meson, which can take part in a strong interaction. And hadron have families, where the members have similar masses but different charges. These families are also called multiplets. So how hadron have anything to do with the Eightfold Way? Well, actually, the Eightfold Way is a classification of hadron particles in a group or geometric pattern based on the same spin and different charges and strangeness number. The number of members of each group can be 1, 8, 10, or 27, but the most frequent is 8. This system was proposed by an American physicist, Murray Gell-Mann, and also an Israeli physicist, Yuval Ne'eman. The name of the system was suggested by an analogy with the Eightfold Path of Buddhism because of the centrality of the number 8. Eightfold Way also means that multiplets with the same spin but different charges and strangeness number are grouped together and become super multiplets. There are many super multiplets, but we'll only focus at baryon octet, mesononet, and baryon decuplet. First is baryon octet. It is a group of 1 lambda that has 0 charge, 3 sigma that has positive, negative, and 0 charge, 2 Z haparon that has 0 and negative charge, and 2 nucleon that has 0 and positive charge. And the total of all the particles is 8. That is why it is called octet. And all of them have the same spin number, which is 1 over 2. So how do these particles are arranged? It can't be random, right? Well, actually, there is a reason why these particles are arranged in that manner. Actually, the horizontal line represents the strangeness number of all the particles, while the diagonal lines represent the particles' charges. Next is mesononet. Mesononet contains 9 particles. Particles in mesononet have the same spin number, which is 0, and this supermultiplet have the same shape as baryon octet, which is hexagonal. And it is arranged the same way as the baryon octet, which means that the horizontal line represents the strangeness number of the particles, while the diagonal lines shows the charges of the particles. Lastly is baryon decuplet. Baryon decuplet consists 4 delta, 3 sigma, and 2 Z particles. And all of these particles have the same spin number, which is 3 over 2. This supermultiplet does not have the same hexagonal shape as the previous two, but instead it has a triangle shape. I'm sure you have realized that I only mentioned 9 particles. What about the last one? Well, actually, when baryon decuplet was introduced, the 10th particle was not discovered yet. However, Murray Gell-Mann predicted that there must be another particle that has the strangeness number of -3 and charge of -1. Then, in 1964, omega minus was discovered, and it has the strangeness number of -3 and charge -1, just as he predicted.